What does America need me to do? So many soldiers are going to go fight. And my grandfather said, America needs you to study. Studied harder than I'd ever studied before in my entire life. From 15 to 20, I was basically just almost primal.
Thank you for being here on the Texas Embassy podcast. Again, we want to give a shout out to the LFG guys for giving us a great studio. But to kick things off, tell us about yourself.
Well, thanks for having me. I'm really excited to be here. So my name is Michael Verhulst. I'm one of the co-founders of CADasCode. My team and I have been working in scientific computing and aerospace engineering and theoretical physics for basically our entire life. I have been in love with American spaceflight and the history of spaceflight for as long as I can remember. So I'm something of a spaceflight historian and an American technologist.
Where are you from originally?
I was born and raised in Springfield, Illinois. We lived in a little house that was the last house on the outskirts of Springfield. So if I stood in the front yard, I could look outside and see nothing but farmland and the rural environment. And if I looked out from the backyard, I would see the city of Springfield, Illinois. So I spent a lot of my life in going back and forth between the city and the rural environment. My grandfather was a farmer. Most of my uncles were farmers and machine shop manufacturing guys.
Wow.
So I was born and raised in basically on the farm. I remember being about 2 years old, and my grandfather would take me and have me ride with him in the combine.
Very cool.
As we would go farm and harvest corn. And at that time, I looked at the massive assembly of the combine, the tractor, as this insurmountable mountain to climb because it's so big relative to my little
machining
size.
Excellence, right? I mean, it's
yes.
Like, wow, the superpower of a machine and how it all kind of came together.
Yes, absolutely. And the attitude was roll up your sleeves and get work done yourself. So my grandfather would be cutting steel all the time, welding up equipment. We'd disassemble engines, work on transmissions.
That's neat. Early education.
Absolutely. It's absolutely super important. Absolutely.
Okay. And so what happened next? I mean, you grew up and then what? Did you aspire to be an astronaut? Like what drove you to where you're at today from that standpoint, growing up at a young age to maybe getting to school?
That's a really great question. So I get that question pretty frequently. I never really aspired to be an astronaut per se. I knew that a couple different things would happen. I knew that there'd be a lot more Americans who would fly in space. And I knew that the commercialization of spaceflight was about to get kicked off. So there used to be really only two ways to be an astronaut. You could go through the military and effectively being a pilot, or you could, in certain scenarios, go through the university system and be a mission specialist if you were academically trained in the right way. But then the third category emerged, which is that the wholesale commercialization of spaceflight. And pretty soon people were going to be able to buy tickets to the moon. So as a little kid, as early as
pretty soon, I think we're almost there yet, right?
Yes, yeah. You could buy a ticket right now. You just won't be launched
right.
yet.
You may not land on it. You may get a little closer to seeing it. Right.
Absolutely. So I was in love with spaceflight since from my earliest memories. Before I could even walk, I was in love with spaceflight. My primary passion was this advanced spacecraft propulsion. The most complicated and most high-energy deep space propulsion systems that anybody can make. I really am deeply motivated to make our society interstellar. So we've got to be able to focus on building the infrastructure and the technology so that we can go to other stars.
So, Michael, very early on in your career, you've gone into the National Capital Region. I think our audience would want to know that. It would give some insight into who you are.
So I was, so when I was a little kid, it's interesting when my uncles and my family knew that I was really interested in spaceflight, and they wanted to encourage me and give me all of the resources I could possibly consume. So I was actually reading a fairly large amount of rigorous material as a little kid, and I was consuming everything I could find. For most of my childhood, I was very uncomfortable unless I had a book with me. I would carry a book with me all the time, which is a little bit interesting because another thing I want you to know that I think the audience might find interesting is that I have dyslexia, dysgraphia, mostly dysgraphia. So that basically means that it's very, very, very difficult for me to write with a pen or pencil on a piece of paper. So in a certain manner, but it's related to being very good at three-dimensional spatial reasoning, which is, of course, related to CAD and manufacturing to machines.
I'm seeing a trace line
space
here.
flight. Yes, absolutely. So at that time, it was, in the late 80s, early 90s, little kids who had dysgraphia, dyslexia had different difficulties. But
Exceptionalities.
Yes. But I pushed through them, and I got to the point where I was reading hundreds of pages of technical material a day.
Wow.
And I think that what you're...
How old were you?
When I was doing that, at a young age, I was taken pretty seriously in physics and astrophysics.
What age?
5.
5.
And then when I would watch movies like Apollo 13 or Contact or even Lost in Space as an esoteric example, and I would be teaching my friends and family what's going on in Apollo 13. How's the rocket working? Why are they doing this? What are the acronyms conveying? Why are they positioning the spacecraft in this way? And talking about things going on in Contact with the Machine Consortium building heavy machinery and wormhole technology and applications of general relativity for deep space applications. And I was sort of teaching that material to anybody who would listen to me. And when I was about 12, I was very, very fortunate to be invited to study graduate level astrophysics and particle physics at the University of Illinois. So I was auditing their program for several years, just staying at the university for hours on end with the professor, being taught as much as I could possibly consume. That was started around 1999, and the reason I wanted to emphasize that is because I was doing that from about 12 years old to 15, and then...
Were you still in high school as well?
Not really. I was technically homeschooled.
Oh, okay.
So I sort of skipped high school,
Sure,
in a certain manner of speaking. I technically have a high school diploma, but my studying was mostly at the university.
Right.
And I think the reason I'm really focusing on it in this way and sort of guiding you in the audience through this, forgive me if it's a little bit of an arduous journey, but I was 15 on September 11th, 2001. And I don't think I'll ever forget what happened. I mean, it was a terrible thing to see. My family was not directly involved. I didn't lose any family members, and I feel very bad for the people who did. But it changed my life to watch what happened. And I knew several different things I knew we'd be going to war soon. I didn't know exactly what that meant, but I knew parts of what it meant. I didn't know who we'd be fighting exactly. But I knew that I was too young, a little bit. I couldn't have enlisted right then, not when I was 15. Maybe soon.
You were 3 years away.
3 years away. 3 years away. And I knew that women of my age would be fighting all over hard. And my mom basically took me out of the university system, and took me to go see Grandpa on the farm. Because it's my parents worked very hard to try to prevent me from being arrogant. And I really respect that and I admire it very deeply. And having these early experiences and being very, very academically promoted can make you arrogant. And it's important to try to resist that. So when I went back with Grandfather on the farm, he straightened me out. And then we just...
A little dose of reality, right?
Yeah, and he'd tell me, so he was drafted to serve in the Korean War and part of the American occupation force, actually, to occupy Germany at the time. So he never saw combat in Korea, but because our forces were split at the time. And he told me the stories of what he and the troops did in the occupation of Germany, and all of these stories as I was becoming a teenager. So my parents periodically wanted me to go back and remember the nature of the reality around it, why we have what we have, what people did for us. And that, okay, so you, Michael, you have these luxuries over here. You're in this university system at a young age. That's privilege, but don't forget why. Mm-hmm. And I would go back there, and it was September 12th, 2011. And my grandfather wanted me to get on the tractor and go mow the lawn. So I just mowed maybe an acre or two of land, and the sun is setting, and I can see it's on a little top of a little bit of a hill, and I could see for maybe felt like forever. And I could see the Midwest, and I thought about what was going to happen to America. And I went back to my grandfather, and I asked him, what should I do? What does America need me to do? So many soldiers are going to go fight. And my grandfather said, America needs you to study. And I studied hard. And at that point, I studied harder than I'd ever studied before in my entire life. I recommitted and got really serious. And from 15 to 20, I was basically just almost primal, with just relentlessly consuming everything I possibly could. Hundreds of pages a day.
It sounds like almost the university ecosystem was limiting.
Yeah,
if you had that.
Yeah, I couldn't get
focus.
I couldn't get enough of what I needed.
So you were at the university still auditing the courses? Were you taking classes or like elsewhere?
Yeah, that started. Yeah, and then getting formally into the program where I could be graded and taught. But grades never really excited me that much. I didn't need that. I needed the experiential learning. I needed to be taught one-on-one. So I did it at that period of my life. I learned from people, everybody we could find, men and women who worked in the Apollo program, the Mercury program, the SR-71 Blackbird program. I was taught a little bit about how quantum computers work and general relativity and how nuclear reactors work. Chief of Naval Nuclear Reactor Operations for aircraft carriers trained me a little bit on the basics of reactor design. And I just ran as hard as I possibly could to learn and be able to contribute to our society and sort of maximize my own skill.
So in your journey right now, how did you, not to take you to the next phase, but,
Sure.
but I'm looking for the trace line of how you ended up in Sweet Home, Alabama.
Oh, yeah, cool. So
and talk about that. People, when they think of Alabama, and you're like, man, we've got a super smart guy here. Has this insatiable sponge-like attitude to learn and continue to learn. Why Alabama? If you could highlight that.
It was maybe a little bit sponge-like, but it's also a huge amount of effort. Mm-hmm. Well, I read the couple days after September 11th, I actually remembered sort of being terrified, not of the terrorists hurting us again. I knew that the American forces would totally dominate that situation pretty quickly. I wasn't really scared in that sense, but I was terrified of the mountain of intellectual material that I really had to learn, because now my grandfather and other people had basically given me this journey to take custodianship of some of the hardest material that we're doing in this country. And I took it very seriously. So that you just sort of look at how do you eat an elephant? Well, you eat an elephant one bite at a time. But I put out this course of what I needed to learn, and I started thinking about what university to finally go to. And the University of Alabama in Huntsville became very obvious to me that I needed to really go to the source, to Rocket City, to where we built the Saturn V rocket, to where engineers were still telling stories of the practical utilitarian reality of what they actually did to get a man on the moon. And I needed to learn that. And I needed to learn it from them. And remember, the scientists at that time they were starting to get older. They were aging out of the system. So I went to UAH in 2005. And one of the things about our team and our company that's really interesting is there's a group of people that have just exactly the right age, where we were born fully saturated into the era of computation, where computation is second nature to us. But we were also old enough that we still could be trained by the old guard, as it were, the original engineers and scientists who worked in the Cold War and World War II and the Apollo program.
The practical understanding, not just the education, but the practicality of delivering on it.
Absolutely. So we were old enough to receive part of it and young enough to receive the other part of the necessary training. So I met Chris and Joe in the honors program at UAH, studying all of the technology that we're so in love with. We really all focused on high energy propulsion systems.
So I think you've articulated, number one, you have this high acumen of of being able to absorb knowledge. But I think you talk to me about the distinction that the United States gave you along that path. I think the audience would love to hear that.
So I was right. Well, it's a composite of a lot of different things. So I was a Boy Scout and got the equivalent of an Eagle Scout rank, and all you know how it is. It's a lot of work, and you're challenged in many different ways. And I got the Presidential Physical Fitness Award because I pushed myself physically as hard as I possibly could. I was offered a nomination by a congressman to go to the United States Air Force Academy, so I was in the academy application process. And then so I went to UEH, studied as hard as I could, was a junior member of the Propulsion Research Center, and helping them, the teams assemble rocket test on these experimental test beds, which is a really interesting story. We should get into like what I did and what they did. It's kind of fun. And all the studying that I'm talking about too, all of this together led to the United States Congress giving me the Congressional Award, which is the highest award that the U.S. Congress gives to civilian teenagers.
For what?
Well, for
what was the award?
Oh, well, so they invited me to Washington, D.C., and I was invited to stay at Georgetown University for a week, and I was given a grand tour with a group of other recipients. I wasn't the only person who received the award at the time, but we were invited to the Smithsonian and to the Capitol Hill. And the staff of the Congressional Award Foundation actually got to a point where they said, Michael, go sit on this bench. Just wait there. 2 Secret Service officers are going to approach you later in the afternoon. And I'm thinking, okay, cool. I kind of knew what that meant, but I didn't exactly know what it meant. And about 45 minutes later, these 2 men approached me in much the way you would think. Big, strong-looking men in fairly black suits, but not exactly a super black suit. And they had an earpiece, just like you would think. And they approached me and they asked me who I was on the particular bench. And I said, I'm Michael Verhulst. They needed me to show some ID. And I did. I identified myself. And it all checked out. And then they escorted me through the halls of Capitol Hill, which is a kind of an interesting experience, and walking in to meet several people. And I was given the physical medal that was made by the U.S. Mint. I was personally given by Barack Obama.
Wow. And what was the award called? Like you were awarded, it wasn't physical fitness.
No, that's a different thing. The Congressional Award Gold Medal.
For what?
Mostly for how much spaceflight history I had been studying. Also for how much volunteering. I volunteered for the X Prize Foundation and for JPL. I worked at Space Camp as a teacher. That was all of this is before the Congressional Award. So, and I wrote a little bit about the risks of the space shuttle as well as a teenager, and talked about how we might lose another space vehicle and might have a loss of crew, but that if we did, America would have to just keep going because we can't actually quit. And I wrote that essay a day before we lost Space Shuttle Columbia.
So this was an essay that you had put together.
Yes.
That you were receiving this award.
Basically for all of it together.
Got it. And what was the title of your essay? Do you remember?
No, I don't remember off the top of my head the exact title of the essay, but it was something about something along the lines of "We can't give in to fear."
That's awesome. Okay, all right, let's get back to UAH in Huntsville, Alabama. You guys, well, let me just turn it over to you because I want to talk about the experience in that environment and what led you to form the team, meet your friends, and now business partners. So let's go back to UAH.
Well, early on when I first got there, I was, a little bit scared that I maybe wasn't going to be good enough because it's such a good school. And the difficulty of what I had embarked on to learn was, at some points I thought it was borderline insurmountable. But I met Chris and Joe basically on day one. Actually, I met them slightly before we matriculated at the university. I met Joe in the summer preview session. By sheer happenstance or fate or divine intervention, pick whichever you prefer, I actually was roommates with Joe when we met. And so we would spend a lot of time going back and forth to the optics building and the propulsion research center and just talking about the philosophy of spaceflight, what you need to do to actually physically build things. And I was a lab technician at the Propulsion Research Center too, and as a junior lab technician, it basically means I'm threading cables through holes in the wall to help people put pressure transducer assemblies onto their rigs. And then
you're not afraid of work. You need to thank your grandpa and your uncles for that. Right.
So I would go up and down ladders and help people hold ladders and rig physical things up and provide equipment, just parts that they would need to build, bolts even sometimes, as the graduate students and research faculty would assemble their rocket engines. This is done in a bay with somewhat similar to the facility you have here. They're thick walls of brick in case one of the test assemblies detonates. You need to isolate it into sort of like a little cell.
Right.
So I believe there were maybe 8 independent research bays. So they have these big holes with a cap on them that you unscrew and then thread the cable assembly through them. And then I took the other end of that rig and plugged it into a computer that was running a National Instruments branded simulation and data gathering equipment to put that into the computational system. So this is all part of the beginning of the relationship between physical engineering and computational systems.
And so you and Joe, and was there another roommate?
Oh, Chris. Chris was, Chris is basically a roommate. He was on the other side of the hallway.
Yeah, that counts. You guys were always together.
Always together, yeah. And we invented a new type of spacecraft propulsion engine. It's basically in the category of a chip thruster. So it's sort of like a semiconductor wafer that looks a little bit like a memory chip or something almost like that Intel would make. And you put it on a printed circuit board substrate, and it sprays liquid helium out of it. And that by injecting high-speed liquid helium under certain conditions, you can get a spacecraft to move through momentum exchange. And it was really very, very new stuff. So it wasn't just liquid helium, it was superfluid liquid helium, chilled to an incredibly low temperature. And we were pressurizing it through a bed of linearly arrayed carbon nanotubes. Because it turns out that if you take a liquid, you can do it with water, you can do it with a variety of different liquids. If you push a liquid through nanotubes, the fluid actually leaves the nanotube at a pretty high velocity. It's in a certain manner of speaking, the interior of the carbon nanotube is very smooth. So, and this is a little bit of a hand-wavy way to explain it, but basically there's no friction with this configuration. So all of the energy that you apply to pressurize the superfluid helium bath is directly converted into a momentum exchange. And this has all kinds of cool benefits. One is the propulsion that's ejected from the rocket engine is really, really cold. And that's very counterintuitive because we're thinking about seeing all these high energy rocket plumes that are burning and on fire in their plasma. And they usually are, but there's other ways to do it. And when you eject a super cold liquid, you can't see it on a normally tuned infrared camera.
Oh.
So
you're doing this at UAH, right? You're working on these problems. So what were you trying to achieve? Like, what was your goal after college, officially?
We wanted to build a spaceflight company and build and sell commercial engines that were higher performing and more capable than any other rocket engine that was available at the time. We wanted to build basically single stage to moon class vehicles where you could fill it up on a fairly unmodified airport and then fly it all the way to the moon and then hopefully fly it all the way back, all with one tank of gas.
Oh, wow. Talk about efficiency.
Absolutely.
Wow.
Really pushing it to the edge.
So is that like round 2? You guys lost that vision and dream?
Well, we didn't lose that vision. It was an interesting thing to do. We took the patents and the idea to build this commercial technology. That would have been 2006, 2007, and then we were invited to research at Argonne National Laboratory and Fermilab to pursue the technology. Fermilab actually has hundreds of tons of liquid helium, and it was a kind of an interesting story. When we were there, we had a meeting with a leader at Fermilab, and he said to us, "Why are you guys here? We don't do rocket propulsion." Well, that makes sense because we were doing very non-traditional propulsion research, and he actually did. At that time when we met him, he didn't really know what our plan was, so he just naturally sort of said, "Why are you here? All I have is hundreds of tons of helium. I don't." You don't need that. Well, no, that's why we're here. That's exactly what we need to do. So we knew a fair amount about the future of
We have a lot of balloons we need to blow up, right?
Yeah. Well, that's
that one big party.
that was a hypothetical risk, actually. And we had a little laboratory that was assigned to our use, and we could have. It was some slightly dangerous. One of the dangers was if we released too much helium, we could maybe we might have to run out of the room quickly because we might asphyxiate ourselves. But there would have been ways to buy a sensor and warn yourself to get out of the room quickly if we had an accident.
All right. So you're doing some crazy things, some fun things. It sounds like you're exploring new territories with this group you met at UAH back in Sweet Home, Alabama.
Oh,
Then what happened after you guys graduated? I know you guys had the vision of this, but you did a pivot.
We did.
What did you pivot to? Help us understand that.
So right at the time we were researching at Argonne and Fermilab, they were investing in what the so-called cloud. And it was actually new at the time, really novel. Some people in the community thought that maybe the cloud would be a bad investment. Well, it turned out it was a great investment. I was invited to help build a major computational infrastructure study on I think it was the Intrepid supercomputer cluster at Argonne around that time. So just being there, we kept learning more about computation, and people got more excited about Python, the Python programming language, just sort of a natural outgrowth of the scientific research that we had already been doing. But we leaned into that really aggressively. Around 2008, there was the major recession, and the economic reality of the world changed significantly. For that period, it would have been almost impossible for us to have a traditional space flight startup where we're trying to build a rocket engine and sell it.
Right.
This was long before anybody really heard names
now
like.
There's probably a bunch of investors that are going to call you just for that idea and to energize that.
It's potentially,
That's the reality of today.
That's the reality. It is the reality of today. And at that time, common names that people throw around today is we all have known Elon and Jeff Bezos, and the list goes on and on and on. They're getting things done, but if you talked about them back in 2008, nobody knew who they were.
Right.
It was a totally different world. So we just had to figure out how to make a little bit of money. Our academic stipends dried up because of the economy. But we had this training in Python and heavy compute. So we did pivot, and we made a consulting company named Terminal Labs. And ever since then, we've been building very complicated heavy compute infrastructure on Python. So we were some of the first engineers to help American companies utilize NVIDIA technology. We worked on jet engine processes. We worked on MRI machine technology. We helped doctors diagnose and treat cancer. We worked on satellite observation platforms for America to help manage data that's imagery data, basically. And then recently machine learning, heavy and data center builds. We also did a fair amount of private equity consulting, helping American companies figure out how to buy and sell each other, mostly focused on semiconductor design. Because what happened is the wealthy family offices and the private equity companies that were thinking about buying a position, they wanted advice on, well, do I buy more NVIDIA or do I buy more Apple? What's going on with this Apple silicon technology? Why is Apple moving away from Intel, investing in their own chips? All of these technicalities were kind of just not really talked about until 15 minutes ago.
Yeah.
And then it became the most important thing in the world. And now you've got Elon talking about the terafab. My team and I actually worked on an early version of that. The need to unify manufacturing and co-design for semiconductors into one integrated platform so that we can ramp up the ability for America to really significantly produce huge numbers of chips.
Yeah, we're here in Austin right now where we're seeing them clear the field to build that.
Yes.
And it's right next to the Tesla plant. So let's go. How did you get to Texas?
When 2013 or thereabouts, we were running our Python consulting company and providing Python heavy compute, that sort of thing. And we were looking around America where to go. We actually wanted to move to a different city.
What was driving that?
We thought that—
Because you're in Huntsville, right, at the time?
At that time, we were in the suburbs of Chicago at Argonne and Fermilab.
Okay, that's right.
And we thought that there were other technology hubs. that were more conducive to the major operation technology endeavors, closer to spaceflight, closer to heavy compute. So we talked together about where to go. We thought about maybe going to Silicon Valley. We talked about New York, maybe Denver. And of course, we talked about Austin as well. And my team, Chris and Joe and I, decided to basically risk everything that we had and just completely just get up, walk over to Austin, and introduce ourselves to the Austin community.
You went all in, all chips in.
Everybody, yep. All three of us just decided to completely uproot our lives and left and then came to Austin to make it work here.
So let's talk about here now. Was it a good move for you? What do you enjoy about Texas?
The weather. No, I'm kidding. There's a lot of things I enjoy about Texas. Yes, it was a great move. We committed to Python early on, and I'm really grateful that we did. We got extremely lucky with that choice. I don't think at that time, 2008, 2013, in that era, I don't think we knew that Python would become the dominant computing language in the world, and it would become used for machine learning and for basically everything else, and that it would become the system of record as well for a large variety of different business applications. And then, of course, it expanded, so it's not just doing compute, but Python is starting to be embedded in things like it comes in Blender, for example. Yeah. And it comes in rendering programs like Keyshot is the scripting language.
I wasn't appreciative of that statement that you made until I saw the documentary that Travis invited me to go see, the Open Teams had.
Yes.
And just to understand the power of that language.
Yes.
And how communal it was in the development or the promotion of it.
Yes.
The use of it, the application.
Yes.
So it's not just the language, but it's a community.
Yes.
That was using it.
It's really powerful. It's extensible. It's easy to learn. It's a great glue language that you can use to integrate and drive any other things. It's pretty good at driving hardware. It's good for robotics and configuration and state management. So when we were running our consulting company, we used Python not only to build applications and write full custom code technology stacks, but we'd also use Python as a command and control and configuration language to basically call into existence heavy compute resources. Right. So the way that works, right, is when you're building a data center or a big hyperscale deployment on something like GCP or AWS, you make a recipe in a dialect of Python that says, well, I need these 7 virtual machines, I need these 4 GPUs, I need this database, and you pick sort of from a menu of what, for example, Amazon Web Services offers, and then you describe that as a recipe, as an ordered set of what you call into existence and how you tie it all together. Without that infrastructure as code management, we probably wouldn't have NVIDIA. It would be unrecognizable versus what we actually have right now. We wouldn't have the hyperscalers, because without these recipe-based and Python-based configuration management tools, the power of these hyperscale compute platforms would be just unmanageable.
I'm going to take you down another rabbit hole,
Sure.
Right? So it's super interesting on what you're working on now.
Yes.
You and Joe. So
yes.
I think you guys have proven you're serial entrepreneurs, successful entrepreneurs. Consultancy is a startup in its own right. Where did you guys see an opportunity with CADasCode?
Right. We saw, that's such a great question, and is really exciting. We're working on basically revolutionizing how
I think what we've demonstrated here in just maybe the first half of the podcast is that you know exactly what you are doing. So when we talk about this opportunity, if anybody questions you or Joe, I fear that question for the person that is being asked to you guys. I mean, you're the experts. You understand this. You have practicality of this. So where is CADasCode and what is the use of it and where are you guys going to take it?
Right. So the basic answer is all of the backstory that I'm elaborating on led to us really coming to the conclusion about 2 years ago of how to fix software-defined manufacturing and how engineering teams basically create CAD models. And what we did is we took the languages that people use to orchestrate heavy compute and what has made and enabled the hyperscalers, we took those same patterns and we lifted and shifted them and applied them to mechanical engineering. So CADasCode is a recipe-based procedural language that for the first time ever really allows machine shop engineers and CAD practitioners and rocket scientists to describe in language the exact shape and form of the part that they need, down to every individual geometric shape.
Okay, let's take a pause on that. Let's educate the audience. What is CAD? Because it's an acronym. And if you could tell us where CAD is in almost everything that is being designed and developed. I think that that's important.
Sure. So CAD is computer-aided design, and it's the software toolkit that people use to describe the shape of a vehicle or a part or an airfoil of a wing. And usually how it's done is in a three-dimensional modeling space. You can do a 2D version of it. That's a little bit older. But with over the last several years, several decades, practitioners who are trying to design physical parts, and I'm looking around your studio here just seeing the manifestation of all of this CAD, because effectively everything in the world has been made with CAD. At some point in the design or manufacturing process, somebody's sitting down on a computer, usually a battleship of a computer, very powerful, very expensive, and they're using pretty difficult to use software that's point and click based, right? So they have a graphical user interface, they have a mouse, and their CAD software is button based. So they see an object, like for example, a three-dimensional representation of this microphone, they see it in the scene. And if they want to change the height of the part, they traditionally have to go click a bunch of menu options, and it's very difficult to learn, and you can't really record exactly what you did. You work with these traditional or legacy CAD programs, and you can spend your entire career doing it. But
I was just going to say, it's a profession in itself.
Yes, it is.
Almost, there's PhD level just folks utilizing CAD.
Yes, absolutely.
Right.
Absolutely. And the more technologically advanced our society is, the more complicated technology we can make, the more we're pushing our CAD technology and the computer-aided tools that we have to use to make what we need next. A few years ago, my team and I basically came to the conclusion that the vast majority of existing computer tools for engineering are at a breaking point. They're being pushed way too hard, and frankly, they're not good enough. So we had to sit back and think about, from a first principles analysis, how do we make new engineering software for American manufacturing? It's got to be different and it's got to be better. So we took the idea of recipe-based descriptions, where you describe the height of the microphone and the width of the microphone, and you put it in a very simple to describe language, and then you can store that in GitHub. So for the first time, we're enabling the world to use all of these process workflow
called prompts, if you will.
Yep.
Right.
And the technology that's been used for 20 years for software engineering, and the advances of high iteration rate software collaborative code design, we can now use that for mechanical engineering.
You want to talk about the power of keeping pace with technology, and especially from a national perspective, we definitely want to be number one.
Yes.
And in order to be able to do that, so are the software, historically, the CAD software, when was the last time it had a refresh? Is that the opportunity that you guys are seeing?
It is the opportunity. It needs. We're providing one of the major refreshes right now. Our technology is getting a lot of good traction. People are really excited. One person came up to us and said, "Your technology at CADasCode is the most important new innovation in the computer-aided design space since 1987."
Since 1987.
Mm-hmm. A decade. This is probably the biggest revolution in decades.
I want to pause because that is are you sure about that?
That
what? That's a long time.
So
nobody's attacked this, or
there have been
people tried.
There have been a few attempts at languages for CAD, but they didn't think about things in the same way we're thinking about the technology. One is that CADasCode is not just a language; it's an engineering platform. So it has computational services and computational co-design. What used to happen is a traditional aerospace engineer would use a very arcane CAD program system to use a computer to design the shape of, for example, an engine. And then they would have to export that file format from that battleship of a workstation computer in this very nasty arcane file format that's unreadable. It's sometimes hundreds of megabytes or even a terabyte of just raw data that is not designed to be read by a human or a large language model. So it's not suitable for like the world we live in today. And the traditional aerospace engineers would be sending these giant CAD model files all over the place, maybe using something like Dropbox as a file collaboration tool. So the way they're keeping track of their version numbers is by changing adding the version number into the file name.
Oh my gosh.
They never used Git. They couldn't use pull requests or check-ins. They didn't have the ability to procedurally lint or verify constraint-based configuration. So if they had a wheel that they needed to get from a supplier and put it on to the landing gear of an aircraft, there was no, what we would consider no modern and suitable way to verify that the wheel and the tire is actually small enough to fit inside of the housing when the landing gear withdraws into the airplane. Just simple things like size and dimensional constraint verification was actually really hard to do with the vast majority of traditional workflows. But if you think about it from a software point of view, you describe in a recipe the exact size of a wheel and then store that in GitHub. So now you can just check by looking at the file directly and it will say that that's a 19-inch rim.
So CADasCode today, what makes it impactful? It's obvious to you, but for the audience, help me understand why we need to, whether it be invest or support this effort to proliferate it and get this into multiple engineers' hands yesterday.
One of the reasons to think about I like the way you're thinking about it. Why do we need this yesterday? Engineers who are working on the projects that they love, like their mind is on fire with creativity, almost to the point of being uncontrollable. Like their mind is a storm. And one of the things that happens is they'll go at home after working and they'll restlessly try to go to sleep, rethinking about the engineering work that they had been doing in the day, reminding themselves of, did I make the constraints correctly? Is it the right size? Is that bolt the right bolt? Do I need titanium? Do I need steel? And sometimes these engineers are doing this because it's a national security crisis. They have to get it right. In certain scenarios, lives are on the line, and they're very committed to doing it right. But then when they roll out of bed in the middle of the night to check their work with traditional CAD program technology, they're just sort of inundated with these giant unreadable files. And if they want to remind themselves, did we pick titanium or did we pick steel? They have to jump through all of these really arcane hoops to get to the point where they're opening a model, zooming in, rotating things with the mouse and the keyboard, clicking buttons, and then showing and hiding layers of a machine stack to get to the particular bolt. And then they click on the bolt and it shows them whether or not it's steel or titanium. CADasCode allows peace of mind to the engineers that are operationally deployed to actually get things done where it matters, and they have to roll up their sleeves and get to work, because everything that they're wrestling with in their workload is just right there in front of them in a human readable description.
So I just kind of want to unpack this, because we've seen a lot of 3D printing. Mm-hmm. We really proliferate out there, the machines themselves. Well, that's an output.
Yes.
Right? So what you're talking about is the design to then get to the print button.
Yes.
And that is time intensive.
Yes.
In itself. So you're talking about this, is CADasCode a compression opportunity of time, and that activity, it's going to be a higher confidence level to hit the print button?
Yes, it gives.
And I'm oversimplifying this. Please expand upon it.
It gives people peace of mind and confidence that they're designing the right mechanical part for the right mission, and it gives them a higher speed to go from design to manufacturing. Because what
order of magnitude would you say?
Well, I don't know. We don't completely. We don't have a lot of empirical data on that through huge amounts of surveys. As a startup company, we're in the process of getting that data. But I was talking about it recently, and easily a factor of 4.
Wow. From 1987, a factor of 4 is still a good factor, even though it's single digits. And again, the more you launch this and get out there, I think the more opportunity is to compound upon that.
The real value starts to come into play when you're designing multiple variants of a platform. The solid rocket boosters that were bolted onto the sides of the space shuttle and their intellectual descendants now that we use for Artemis, the space shuttle versions of those had 120 different design configurations. It's not so much that you could buy 120 different options, but the design team making them had 120 different variants they had to choose from to figure out which of those is the optimal variant. Each one of those has to be simulated, verified, iterated on, and then looped back to the design team for committee review and analysis. Those design loops are traditionally just way too slow. With CADasCode, all of those steps from simulation to machine ability studies are just done on one platform as one integrated end-to-end solution.
I love that you use that as an example because those guys are on their way back home.
Absolutely.
Successfully.
Absolutely. Right now, as we film this, they're in space. So they just got about 72 hours ago, they were the furthest humans to ever fly.
Yeah. And the president spoke to him.
Mm-hmm.
Yeah.
So they're not back yet. But they're coming back right as we speak.
No, but that was a great example, right? I think it resonates in the complexity of the design. You definitely want that because unfortunately we've seen where a miscalculation has had a catastrophic effect. The Challenger.
Yes.
In fact, there's a school, elementary school or high school named
Challenger Learning Center
in Huntsville, Alabama.
We need them for drones.
Yeah, there's multiple applications for this technology. What other industries do you see this?
Architecture, construction, business information management, and semiconductor design. Semiconductor packaging and also semiconductor fabrication layout, just orchestrating how you arrange your manufacturing equipment in the job shop is the sort of thing that's really great to do with a recipe-based CADasCode-driven configuration language.
And so you guys are looking to raise, how would that speed things up for you guys, or what are you thinking?
Oh, massively. We are, yeah, right. We're talking with institutional venture capital right now, trying to raise a seed round, and it's basically just the funding is basically just pure acceleration. A lot of what we need to be doing right now, we can do in parallel, which is a somewhat unique. It's not completely unique, but not every startup can actually do things in parallel. We can because we can set up teams of software engineers to take domain responsibility for aspects of what they have to build, and we're ready to sell to enterprises right now. We have the minimum viable product. It's working pretty well. It's good stuff, and we're ready to just completely expand this opportunity and really race to get this out there. And one of the reasons,
I like that you just said race because offline, not to be mentioned here, that is a distinguishing customer that wants to talk to you in that industry.
Yes. Yeah. We're pretty quick, but we need to continue to be quick. And America needs this technology now. And like you said, we need it yesterday. Another thing I wanted to emphasize is it's really great for large language models because this huge investment in AI systems has really sort of neglected three-dimensional modeling. Most of the technology we have in the machine learning and AI space is not good at making a 3D part. Certainly not good at something that can actually be manufactured.
No, it's not. It's not commercially available, quite frankly, right?
Right.
I've attempted that archaically, right? Through vibe coding, trying to take an image, 2D, look at it 3D.
Yeah.
With coding. So the systems are not out there. We may think they are, the GPT models, none of that. Especially with the reliance of building it.
Yes.
And actually manufacturing
Right.
it and having some level of human connection.
Absolutely. No, absolutely. They'll hallucinate in really weird ways. So the current systems will sort of cut the back off of a model.
Yeah.
Because a lot of them are basically extrapolating from a 2D image.
Yes.
Where often the 2D image itself was made through Gen AI processes. So it's an extrapolation of an extrapolation.
I bring that up because, some folks would say, oh, well, just let Claude come up with this pretty soon. Or why aren't those companies looking at doing this at speed? So what's the difference between you rolling this out and waiting for Claude to catch up?
There's a possibility that the big foundation models they're going to probably be very interested in what we have. I don't know that for sure, but it seems very likely. What they have done is basically taken all of these triangles, hundreds of thousands or millions of triangles in a 3D scene, and they're just trying to statistically predict where all those triangles are going to be. So if you ask a foundation model to give you a rocket ship, it'll just throw a bunch of triangles in a state's space, and it might look terrible, and it's almost certainly not going to be manufacturable. But CADasCode describes the design intent of the exact geometric configuration of what you want in a human-readable language. And the benefit of that for machine learning is all the foundation models have been trained to be specifically large language models. They want to read and write human language or something that's very similar to a human language. So one of the revolutionary aspects of what we're bringing to the market is you can think about this CADasCode technology as an intermediate representation. The large language models don't know that exactly that they're looking at CADasCode code. They sort of just think they're looking at human speech, or they think they're looking at just more Python or more JavaScript. But there's so much Python and JavaScript that they've already been trained on. The foundation models are currently very good at just generating CADasCode intermediate representation script. And then when our platform technology turns that directly into a manufacturable part. And that step, going from the CADasCode script to producing the manufacturable part, that's not Gen AI. That's a procedural exact transformation. And one of the reasons we're so excited about that is because it means that when we send the final representation of the part to the machine shop, they'll build what needs to be built.
And it's ready for print.
And it's ready for milling, ready for printing, ready for casting.
Ready for use.
Yeah, absolutely.
Well, Michael, number one, I'm happy that we have great Americans like you working on this problem set, especially when you say since 1987. I think the mission that your grandfather gave you, I see you playing that out. So kudos to him for giving you that mission. And thank you for asking him that, because I know without you and your team, I haven't heard these type of technologies being at the forefront. It's an assumption of mine. So I'm happy to be a part of your journey as well.
We need you. We really appreciate all your help. We needed it.
Yeah, we'll put in the descriptor, everybody, how they can connect to you and potentially support what you're doing. It's very much needed. I know it's not the sexy end item, right? The jet, strike fighter or the stealth aircraft, but it is so important to have these type of systems, especially here in Texas, especially here, for national use.
Yes.
Here in the United States. So thank you for taking that charge.
Thank you.
The last thing that I will ask you is, and I've asked everybody, is if they could give themselves a call sign to kind of describe what they're doing and in a variety of ways, what call sign would you give yourself for this particular mission?
I'd call myself Underhill.
Underhill. Please expand.
There's a wonderful novel from the novelist Vernor Vinge called A Deepness Upon the Sky. And one of the protagonists in the novel is named Sharkaner Underhill. And he basically was a scientist and engineer in sort of a metaphorical world where they're in something along the lines of World War II era combat. It's a mid-20th century technological development. And he was the primary scientist of their society who led their country to a couple different things. He led them to win the war without a single shot being fired. So he did it in an incredibly strategic and brilliant way. And then he also led their society to be spacefaring.
Love that. That is a good descriptor of where you're at right now. I love it. Thank you again for joining the podcast. We hope to get you back and hear about all the success that you and CADasCode team are having.
I'd love to come back. Thank you so much.